All right. So imagine you have a beam like this one, and in this beam you have the effects of bending, right? You have a bending moment here, M plus dm on this other cross section. So basically what I'm saying is that when you move from this section of the beam to this section of the beam, there is a change in the bending moment, right? That's why this dm is there. Also, you have the effect of the transverse shear forces. This transverse shear force V, right? So you have this transverse shear force acting on this cross section. What is going to happen is when you move to this other cross section, you have basically V plus dV, or you have a variation on the transverse shear force, right? So these are the two types of loading that we are going to consider for the analysis of the transverse shear. The effects of the bending, right? You have a lot of bending. Imagine a wing, for example, right? A lot of bending. And you have also transverse shear force. The lift is a transverse shear force on the wing, right? So these are the two major loading effects that we have in aircraft structures, and we are going to consider these two things, right? Okay, so what we are going to do is, I'm going to take now from this beam, I'm going to take this small element that you see here, and I'm going to consider it, I'm going to isolate it. If you want, I'm going to do a kind of a free body diagram of this element, this shaded element, and I'm going to consider all the internal forces that are acting on this element. And like I said, we have what? We have bending stresses, which is a direct stress. So these stresses that you see here, I'm going to highlight here. This stress distribution that you see there is a linear stress distribution, right? A direct stress along the longitudinal axis of the beam. So you have the neutral axis here. So this is the neutral axis, right? So at the neutral axis, the bending stress is 0, and then it rose, and in the top fiber or surface of the cross section, you have the maximum bending stress, right? It's a direct stress. So in this case, we have above the neutral axis, we have a compressive stress or a negative stress, and below the neutral axis here, you have a tensile stress, right? Or positive stress. This is due to the bending effect. So, now what we are going to do now as well is we are going to look even further to this element now. I'm going to take this element now and I'm going to do a free body diagram of this element here now, and again represent all the stresses that we have there. And starting again with the bending stresses. So in this cross section here, so this cross section here refers to this cross section here below, okay? Oh, let me try to make it a bit better so I can delete this, right? And I can say, so this cross section here corresponds to this one here on the left side, huh? And then what I have is, in this cross section, I have a direct stress due to bending, this sigma XX, and I have a transverse shear stress, which is this one that I call tau XS. So this S, basically, S is this variable here. So is a local variable, if you want to call it that way, that starts, in this case, on the top surface of the cross-section and comes all the way down until the bottom surface of the cross section. Okay, so we can say that this from here to here is an infinitesimal length ds. Right? So I can do it even better, I think. Let me see. I can zoom in this element and say, so this length from here to here is dx along the longitudinal length of the beam, and this length from here to here is ds. Okay? So we have this shaded volume element here is the dimensions of this infinitesimal element. They are there, and we have all these stresses acting on this element. So going back again to the stresses. So we were talking about the bending stresses, right? So bending stress in this cross section is sigma xx, but what happens is when we move from this cross section to this other cross section, my bending moment varies from m to m plus dm. There is a variation on the bending moment. So this means we will have also a variation on the bending stresses, right? Makes sense, right? Don't forget the bending stresses. You can see this equation from bending. The bending stress, sigma xx, is a result of the bending moment we have on the beam, right? These m's that you see there on that equation is the bending moment along y-axis on the cross-section and z-axis on the cross-section. And of course you also have second moments of area, product of inertia there, right? So it's the geometry of the cross-section you are using in your analysis. So the bending stress, this one, sigma xx, is a function of the bending moment. And what happens is, if the bending moment varies, when you move from this cross-section to this other cross-section, you have a variation on the bending moment. That, of course, will be reflected on the variation of stress, right? And the way we describe that variation of stress is this term here. So this term here, we can say that this term is equal to a variation on the sigma stress, sigma xx. Right? Taylor series, approximation from a Taylor series, we can say that sigma xx is the derivative of sigma in order to x times a delta x, right? And we can do the same analysis for the shear stress. If you look carefully from this figure, in this cross section here, I'm going to use the red color now. In this cross section here, you have a shear stress tau sx. I think you remember these subscripts, the meaning of these subscripts. Why is tau sx? Don't forget, this is a shear plane whose perpendicular to this shear plane is my s variable. Right? So that's why the first subscript is an s, is the normal to the shear plane, which is the same direction of s. The second subscript, x, means the direction of the shear stress, of the vector shear stress, which has the direction of x. Right? So I'm doing this a little bit fast because you did learn this already in year 2 in solid body mechanics. So what is going to happen now to the shear stress when we move to this cross section here below? When I move to this cross section now, what is going to happen to the shear stress is, I'm going to say, is equal to the same shear stress in the previous shear plane, tau sx, plus a variation on the shear stress. Because we are moving between two shear planes, and when we move, we assume there is a variation, in this case on the shear stress. So you can say that this is equal to a variation, in this case, on the shear stress, tau Sx. Okay? And same thing happens, we can do the same analysis, considering now this cross-section here. We have tau xs is my shear stress, and when I move now to this another cross-section, I have now tau xs plus a variation on my shear stress, tau xs in this case, right? Okay? So, a summary of what is in this picture and on what I just discussed with you is basically, so what we do is, on our beam, we consider a small infinitesimal element, right? We consider this small infinitesimal element, so we zoom in this element here, and then in this element we consider even a smaller one in the cross section, this one, and then we zoom in this element over there, and then we do a free body diagram on this element and include all the stresses and the variation on that stresses when we move from one cross section to another cross section, right? And as you might be guessing now, what we are going to do now is we are just going to write the equilibrium equations for this element, summation of forces in the x direction equal to 0, right? And then let's see what we get after doing that. So like you learned in year 1 and year 2, everything is in equilibrium every time. So let's do that. Let's write the equilibrium equations and see what we obtain at the end. So I'm going to clean this a little bit. So let me delete all of this stuff. Right? And let's zoom in. Let's focus on this element here. So let's zoom in this and start writing the equations here, okay? I'm going to use the red color, see if it works. All right, so let's start with summation of forces in the x direction equal to 0. Let's start writing these equilibrium equations. So let me start with this. Let me start with this stress first, all right? So we have this stress we have this stress that is acting on this shear plane. So I need to have a force because I'm doing the equilibrium of the forces. So I have the stress sigma xx. I need now to multiply this stress with the area of the cross section, or the area of the shear plane where this stress is acting in. And that area, so I said before that this distance from here to here is an infinitesimal distance ds. Right, so I can multiply this by ds. And then I need to multiply by the distance along the width of my cross section. And I'm going to say that distance is t, is a thickness, let's say that way, okay? So basically this term here, I can say that this is an area. If I multiply S by T, I will get the area of my shear plane. If I multiply this area by my direct stress, sigma xx, I will have a force in the horizontal direction, right? So I can do the same now for this cross section here. I can do the same for this cross section. Now in this case, I will have a negative force, right? Because look, this stress here is opposite to my positive x-axis. So what I have to do is, I have now to say, so my stress is sigma xx plus derivative of sigma xx dividing by x times dx. So this is the stress. Now I need to multiply again by the area, which is ds times t. Right? You don't need to rush writing everything I do, because that's why I'm recording this. Okay? This video is going to be available to you. It's better if you try to understand, pay attention, make questions if you are not following it. Because this all will be available to you. Even the derivation is going to be in your textbook in Blackboard, okay? So, don't worry. All right, so the direct stresses. We did the direct stresses, so that is done in the x direction, but we still need to consider now the shear stresses. Because if you look at these shear stresses here in the horizontal direction, this one and this one, they also have a contribution for the force in the horizontal direction, right? So we need to include them in the balance of our forces. So I'm going to do it here, and then I will just move to, so let's do it here. The contribution of these shear stresses, I'm going to start with this one. So I have, this one here, I can put this way. So it's going to be a negative contribution because it's opposite with my x-axis. So shear stress, right? I need to multiply this by the area of this shear plane here. This shear plane. So this is dx, right? Agree with me? And I need to multiply now by the thickness t. So I get the area. Area times the stress gives me a force. And now I need to consider this contribution, which is going to be a positive one, as the same positive direction as my x-axis, right? So I need just to write down the entire stress, which is tau sx plus derivative of tau sx in order to my s coordinate. And I need again to multiply this by the area, which is dx times t. Right? You all agree with me? These are the contribution of these two. So what I can do now, let me see if this works. I need now to move this all the way. So let me see. If I select this. Ooh. Not good. I think maybe I can do it this way. Yeah. So, oops. Sorry. I think if I zoom out a little bit more, yeah, it might work now. So I need to move this guy here, right? Very good. Right, so this is all we have. Let me just delete this one here. So summation of forces in the x direction equal to 0. So this is all the forces we have in the x direction. Agree with me? So the result is that this needs to be equal to 0. Yeah. Right? Is correct? Is it correct? Yeah.
You forgot the ds in the last bracket.
ds?
Yeah. D tau sx in brackets.
Oh, you're right. Yeah, I can fix that. So I need to delete this one here. is not, yeah, is ds, right? So you are saying this one, I forgot this one, right? Very good. Yeah, you are paying attention, very good. It's a very good way to check if you are following, yeah. All right. So this is the balance of the forces in the horizontal direction. I think we can simplify some bits here. Let's see, let's start with this. So I'm going to use the blue color to delete some stuff. So look, this one will cancel with this one, right? Agree with me? Right, look at this. Minus sigma xx times ds dt. So I would say this will cancel with this one. What else? I think something will going to happen to the shear stress as well. I think this term here will cancel with this one, right? Agree with me? So this will cancel with this, right? That's it. That's what we get. So what I can do is, so the terms that I will get is this one here. I'm going to write it down here again. Right? And now I have this other one plus derivative of the shear stress You all agree with me? So this is the final result that we have. Just going to confirm here to see if everything is fine. Everything is fine, but we can even simplify a bit more because this term and this, they cancel as well, right? We have equal to 0, so we can divide everything by this. And then at the end, we get this final result, which is minus the derivative of the bending stress plus the derivative of the shear stress equal to 0. A very important achievement from a very basic equilibrium equation, summation of forces in the x direction equal to 0, right? Okay, so this is a first achievement in our derivation of the equation for the transverse shear flow. The other thing we have to do now is I have to introduce now the concept of a shear flow, which basically is a force per unit length. So shear stress is a force per unit area of the shear plane, right? Shear flow is a force per unit length. So I can say that my shear flow, let me just use the same notation, yeah. My shear flow, I will define the shear flow by this Q variable. Shear flow Sx is going to be equal to my transverse shear stress times a thickness. All right? So if you look at the units, this is quite easy to understand. So look, shear stress, the units, Newton, square meter. Thickness, unit is meter. So the result is a shear flow Newton per meter. Right? Is a force per unit length. And we are going to talk a lot. So until the end of this model, we are going to talk on shear flow. Not shear stress, shear flow. But the stress is very easy to obtain from the shear flow Q. You just divide shear flow by the thickness. Then you get the stress, all right? This is also, I know that some of you are doing projects, structures, and using abacus, finite element analysis. So what you get in these packages is the shear stress. What you will get from the analysis we are going to do here, shear flow. But you can easily convert between these two by just dividing by the thickness, all right? Then you can compare in your projects if you want. You can compare that, right? So shear flow. And what I'm going to do now is I'm just going to replace. Basically, or before that, I can just say that I will do the following. I will replace my shear stress with the shear flow, or if you want, I can, if I multiply everything by the thickness, what we'll have is minus the thickness, derivative of direct stress, plus times the thickness right? So this is times the thickness. And this term here is this, right? Is my shear flow. So I can replace this term with my shear flow. And this equation, we need to keep it, right? Because what I'm going to do now is basically just work a bit more this direct stress from bending. So what I'm going to do now in our following derivation is I'm going basically to replace this direct stress, sigma xx, with this big equation over there. Don't forget, direct stress is a result of the bending we have on our beam. The equation from bending, unsymmetric bending, is this one. So what I have to do is I just have basically to make the derivative of this direct stress, as you can see here, right? I just need to do the derivative of the direct stress in order to x, and then put in this equation. And that's exactly what I'm going to do, okay? So, what I'm going to do is, I'm going to do the derivative of this direct stress in order to x, right? So, in order to do that, in this equation you have second moments of area, products of inertia. They are constant. So, the derivative is 0. The only thing, when I do the derivative, the only thing that is going to be changed is this term, which I will have the derivative of this term in order to x. This term as well, I need to replace it by the derivative in order to x. Same thing for this term. And this term, derivative of the bending moment in order to x. Right? Okay? So, that's the only, when I do the derivative of the direct stress, the derivatives on the right hand side of this equation that I need to do are just the derivatives of the bending moment in order to x. And the good thing, the good news, is that you know that these derivatives, they are equal to the transverse shear force. You know that from year 1, right? When you did the bending moment and the shear force diagrams, remember? It was me who did that with you.
Yeah.
Year 1, no? Yeah, I think it was. Not for the placement people, right? Placement, I think it was a different one. But anyway, so you know that this term, what I'm saying is that this term here is equal to the transverse shear force. This term here is equal to the transverse shear force in order to my y-axis. This term is equal to the transverse shear force in order to my z-axis on the cross-section. Right? So basically, what is going to happen is, in fact, what is going to happen is, I need to replace these terms with the transverse shear with Vz, Vy, Vy, Vz. And then if I do that, I will get what? I will get this term here, which is the derivative of the direct stress. So I just need to replace that with the transverse shear stress, right? Okay, so I will try now. So let's see the best way of doing it. So I will try to delete this bit here. I will keep this one. Okay. And what I'm going to do now is I'm going to replace this derivative of the direct stress. Am I going too fast? Are you following, or more or less? Okay. We'll do some examples, okay? Don't worry. I'm just trying to get the final equation for the transverse shear flow, and then we will apply that final equation on many different examples, okay? But I think it's good to understand where the equations come from. I always like to do that. I don't want to give you only the final equation. That is not good. All right, so let's do that. Let's try to replace this now. Oops. Okay, so we will have what? We will have T I'm just copying all of this. Right? This Z that I just put here, this Z is the distance of the shear plane to the neutral axis of the beam, right? In the Z direction, of course. Right? I don't know if you remember that from bending. That's what this means. Oops. Now we have this term here. Oops, sorry. Right? Times distance y. And now what we have is, I need to add this term plus the derivative of the shear flow in order to x. This is equal to 0, right? It looks like it is okay, right? So I'm just replacing here this derivative and multiplying that by minus t. So that's why we have plus t. Looks okay, right? Right? Now we just do a bit of rearrange this equation. So basically what I have now to do is I can move this t. So I'm going to try to point out. I can move this t to here. Same thing for this t. I can move it here. Right? maybe I can do it here. Let's see. So maybe if I find some space here, I delete this one, and then I just do TZ plus, and now here I just do TY, right? And then what I can do now, I'm going to do this. Next step is I'm going to send this shear flow, the derivative of this shear flow, to the right-hand side. And then I need to change the signal, right? So what I'm going to do is I'm going to put a minus here. This one goes minus as well. And this guy now goes to the right-hand side. So I'm going to put it like this. I'm being a bit lazy, right? You might say. Okay, that's it, right? You agree with me? And now, what we are going to do now is, so don't forget that our target, our aim, is to obtain the shear flow. Our aim is to obtain the shear flow, this one. This is our aim, right? So what happens is, I have here, in fact, there is an error here. I just detected. This is not derivative in order to x, right? Look at this term here below. Is ds. Right? So this is, sorry, there was here a mistake. I'm fixing it now. This is the derivative in order to s, not x. This is correct. So what I'm going to do now is, I want the shear flow, but I have here the derivative of shear flow. So how do I get the shear flow? I need to do the integral, right? So what I'm going to do is, I'm going to do the integral right-hand side. So it means I will have to do the integral on the left-hand side as well. Okay? And I'm going to do this integral in so from S0 to a generic variable S, in the S direction of my cross-section. All right?
So,
yes?
shouldn't the ty be positive, that term?
Which one?
The ty term, the second term.
No, but we sent the shear flow to the right-hand side, so that's why then it becomes negative, right? Don't you remember that step? We had everything positive, right, on the left-hand side. And then I isolated the derivative of the shear flow, so I send it to the right-hand side, and I need to change the signal.
I mean, the ty term.
Yeah?
I multiplied t by the term above was negative.
You are saying this term here? This term?
Shouldn't be positive and not negative.
No, it needs to be negative. Because, look at this equation. I'm going to delete this, okay? We use this equation, right? So in this equation, we want to calculate the derivative. So we make the derivative of the bending moment, and then we get the transverse shear force, right? In this equation, everything is negative here, right? Minus, right?
I didn't see the negative in front of it.
Yeah. Okay? Yeah. All right, good. All right, so if I do this right-hand side will become, basically will become my shear flow. I'm going to write like this: QSX minus Q0 SX. 0 is the initial shear flow. This is because of this lower limit of the integral, right? So when you integrate, this term here is because of this limit of the integral, and this one here is because of the lower limit of the integral, okay? So we will have something like that when we do the integral of a derivative, that it becomes equal to, in this case, to the shear flow, right? So I can just replace all of that. So basically what we are going to have is, I will have my shear flow. I'm going to drop the subscripts on the shear flow minus the initial shear flow. Right? And this is the final equation that we need for the transverse shear flow. So I'm going just to so this equation that we have here on this box will give us what? This is what we are looking for. This is the shear flow in a section located at a local distance S. In this case, our S, look at this, don't forget this, our S variable, this one here, we define this local variable starting on the top surface of the cross-section, right? So the S0 is at the top surface of the cross-section. And then when this variable is equal to S, we are at this cross-section, and the shear flow at this cross-section is given by this one here. Right? So this is the initial shear flow. In order to do the analysis, like we are going to see in the examples, we need to know this initial shear flow. So this initial shear flow will tell us where our local variable S will start, the origin of this S variable. So in open cross sections, like for example, sections like this, in I shape, L shape, U shape, H shape, the shear flow, initial shear flow, we always choose free edges. So we say, okay, I will start my analysis in this free edge. So my S local variable will start in this free edge. Why? Because in the free edge, in this shear plane, in this cross section here, my initial shear flow, Q0, is equal to 0. Right? And so this is how we are going to solve these problems. So we always start from these free edges, because we know that this initial shear flow in that case is going to be equal to 0. And then we define the origin of our local variable S, where it starts. And then the only thing we need to do then is just to do this integral. And then we get shear flow at any cross section that I want. For example, imagine I want the shear flow. So let me delete this. Imagine, for example, that I want the shear flow at this section of my beam. What do I need to do? I need to know this distance from here to here. Let's say, for example, imagine, just an example, this distance is 100, for example. Okay? And then I solve these integrals. I replace this S here and here by 100. And then I get the shear flow at that section of my beam. Okay? So what I propose is, let's see now on the second half of the lecture, let's apply this in 1 or 2 examples, and then we go. What do you think? Okay. So let's do a break, 5-7 minutes maximum. Let's start the second half of the lecture. So I just copied the final equation we derived, and we are now going to use this final equation in some examples. one or two maximum. I will start with a very simple one, a very simple cross section. So I suggest if we do something like this, a rectangular cross section. Okay, so let's say this, let's put some dimensions here. Let's call this height H. Let's say the width T. Okay. So this is a very basic, simple geometry. You know the neutral axis is going to be here. So what we can do is we can put here a coordinate system. Let's say this is my z-axis, this is my y-axis, and x direction is in the longitudinal direction of the beam, right? So this is a cross section. What you have there is a cross section. And we are going to apply this equation to obtain the shear flow in this cross section, right? So what we need to do, of course, I forgot to include here, we are going to assume that we have here a transverse shear force. This one in blue. This is a transverse shear force that I will say it is Vy. Oops, sorry. Not very good. Vy. Okay? Imagine this, for example, it is like the lift in a wing, for example, right? Our transverse shear force. So I want to know, imagine this is the cross section of your wing. It's not, of course, it's very far away from it. But imagine it is. I want to know the distribution of the shear flow in this cross section. Okay? Why do we need, for example, shear flow? Why do we need to calculate shear flow? You might be thinking. Imagine, for example, that we have something like this. That we have this cross section here, this beam, okay? And imagine that in top of this we have a plate, for example, right? And we need to bolt this plate with rivets or whatever to make the connection of this plate with the beam. We need to put some rivets here. And then why do we need to know the shear flow? Because the shear that is flowing in this cross section is going to be the same shear that is flowing along this joint. Why is that? Because imagine if this is my shear flow QSX, this is going to be my shear flow QXS. And we know from your stress analysis in year 2 that these two from symmetry, they should be the same. So we are going to calculate this shear flow, but in fact we are going to use this shear flow, for example, for the calculation of the pitch of the rivets, the diameter of each rivet. So we need this shear flow, this information. And you have this a lot in aircraft, right? You have rivets everywhere. So we need to know the shear flows very well, how they are distributed along the cross section, the wing, how they flow. That's why we call this shear flow, how they flow through the wing, right? So we need to do that. All right. Okay, so let's start our analysis then. So we are going to apply this equation for the shear flow. But before we just start replacing all these second moments of area, products of inertia, everything, don't you think that we can simplify this equation a bit more for this particular cross section? Because we have a symmetric cross section, right? This rectangular cross section is symmetric. So it means what? It means for example, it means that my product of inertia, I, y, z, when we have a symmetric cross section, is equal to 0. Right? So that simplifies a lot. You have here, in this equation, for example, you have here product of inertia, which is 0. This one is 0 as well. So what I can do is, I can, based on this simplification, I can try to rewrite here a bit this equation. So we will have what? We will have before that, there's another thing we should look at. So let's look at this second moment of area, this one, and this one. So we have second moment of area about the y-axis and about the z-axis. Do we need to calculate both? Look at this equation. This second moment of area is multiplying IZ is multiplying VZ, the transverse shear force in the Z direction. Do we have any transverse shear force in the Z direction? No. So that will be 0, right? VZ is going to be 0. So I don't need to calculate IZZ, second moment of area about the Z-axis. I can do, if you want, but it's a waste of time because it will be multiplying 0. You know, this kind of analysis is important to do before you start just doing calculations, especially in your exam, right? Before you start doing calculations, you need to do this kind of analysis. So we will definitely have to calculate the second moment of area about y-axis. We will have to work this. We will need this. Sorry. Is not correct. Is not correct. I'm coming back to this term. So what I want to say now is, let's see if I can undo this. I can. Yeah. So what I want to say is, if you look at this first integral here, this one, so this term goes away because the transverse shear force in Z direction is 0. This term also goes away because the product of inertia is 0 from symmetry of the cross-section. So I don't need to do this integral at all. That will be all 0, right? So I only need to focus on this one here. Okay? So that's what I'm going to do. So I'm going to undo this just to keep this initial equation. So I'm going to focus on this one. So I'm going to write it down here again. Minus integral S0 to S. So I can say that this term, product of inertia, and this, they are 0, right? So at the end, I will have only what? I will have the second moment of area about y-axis times Vy dividing by Izz. Agree with me? And this term is going to multiply the thickness times this, and this is going to be equal to shear flow minus the initial shear flow, right? Okay, you all agree? Are you following this? So, but I can even simplify a little bit more. I can say that this second moment of area about my y-axis, they cancel, right? So I can say that at the end I will have only Vy dividing by Izz. That's why I did some mistake before, because I said the only second moment of area we need to evaluate is Iyy, and in fact the only one we need to evaluate is Izz, right? So that's what we have to do. We have basically to calculate the second moment of area of this cross-section about this z-axis that we have here in the figure. This one, right? Oops.
So
What IZZ isn't zero?
Sorry?
IZZ isn't zero.
IZZ is not zero.
Okay.
IYY is not zero as well. So basically, the second moment of area about z-axis is given by, I think you know this equation very well, right? Is, I can write it here. So IZZ is given by the width of my cross section, which is t, times the height power 3 divided by 12. Right? You remember this equation? It's been a while, yeah. But anyway, this is something you can find, in books. You can find in the appendix of many books. You can find these inertia properties of cross sections, right? Same thing for the second moment of area about my y-axis. In this case, the width is going to be h, and the height is going to be t, and then we have to do power 3 again, dividing by 12. Right? I'm quite sure you guys can quickly now remember these second moments of area. Well, like following your question again, none of these are zero in this cross section, right? In this geometry, they are not zero. But the only one that we need for the shear flow is IZZ. We don't need IYY. That's the thing, right? Okay, so what I'm going to do is I'm going to replace now IZZ over there. And then we will have what? So let's see what we have at the end. So before I replace, I think I need to introduce another thing that we are missing here. I'm just going to move this a little bit to the left because I need here. So we are doing the integral in the S direction. So this needs to be the S. Right? What I need to introduce and what I forgot to introduce is the local variable S. This is extremely important. Right? We need this local variable S because we need to define the lower limit and the upper limit of this integral. So we need to know the direction S. Direction S is the direction of the flow of the shear flow. It will flow through S. And what I'm going to do in this example, for convenience, I'm going to say my S variable, it will start here at the top. At the top of my cross section, top fiber of my cross section, okay? Why am I doing this way? Because if I do this way, this initial shear flow is going to be equal to 0 because the top edge is a free edge. We don't have transverse shear in free edges, right? They are 0. So, and the only thing I need to do now is to do this integral, but there is still a problem, which is this y distance, this y variable that we have here. We need basically to write this y variable in terms of our local variable S. This is, if you understand this, you will solve these problems very easily. Because don't forget, we are doing the integral in the S direction, right? So integral is in ds. So we need to see how this y changes with S. So for example, let's do something like this. Imagine I want to evaluate my shear. Oh, let me use the red, I think it's better. Imagine I want to evaluate my shear flow in this cross section here. This cross section here at a distance S, a generic distance from my top surface. This y in this equation is the distance. Basically, this y is this distance I'm going to represent here from this cross section to the neutral axis. So this is my y. Right? this y and z that you see in this equation for the transverse shear flow, y and z that you see there, is always the distance in the y and z direction to the neutral axis of your cross section. So from this, I think it's not very difficult to obtain this y. We can say, for example, look at this. Look if you agree. I can say that this y variable is going to be equal to h over 2 minus s. What do you think about this? Do you agree with this or not? So h over 2 is this total distance. If I remove this s, I will end up at this y distance, right? And this here, you can see there is a relation between this y variable and s variable. You always need to get this relation. Even if y is equal to a constant, doesn't matter. But you need to know also the value of this y variable, all right? And now, yes, now we are in very good conditions to just do the integral. So basically, look at this. This Vy is constant in the integral. I can send it outside of the integral. Second moment of area, Izz, is also constant. When I do the integration, I can send him outside of the integral as well. The thickness, T, is also constant, right? Look, when you change S, your thickness is always T, right? Always T. Agree with me? So it's also constant. I can send outside of the integral. And then I can say that this integral will be minus Vy over Izz times the thickness, right? Now times the integral from S0. S0 is this point here, which is equal to 0. Right, is the beginning of my S local variable, which we say is 0 there. So the lower limit is 0. The higher limit is going to be a generic variable S. And then I just need to do the integral of this y variable, but I know that this y variable is h over 2 minus s. And I know initial shear flow is 0. This is going to be my distribution of the shear flow, which is going to be a function of this local variable s. My shear flow is going to be, depending on this s variable, I will have a different value for my shear flow, right? And this is quite easy to do. Now, you just need to do that integral, which is not difficult, I think. So you will have here h over 2 times s minus s squared over 2. This is going to be equal to your shear flow, right? So this transverse shear force is given. Second moment of area is just calculate from that equation there. Thickness of the cross section is given. The height of cross section is given. And then what you have here is a quadratic function of the shear flow with S variable. So let's do some checks. So I'm going to delete a little bit here. Let's see, erase. So I'm going to delete, I need some space here. All right, so I'm going also to delete this one here. And I'm going to delete this one as well. All right, let's focus on this equation and let's get the value of the shear flow at 3 points in the cross section. So the first point I suggest is, I'm going to use the green color. Let's get the shear flow at this top fiber or section of my cross section. So that point is S equal to 0. So if I replace in this equation S by 0, I get what? 0 minus 0 is 0. Shear flow is 0 at this point, which is correct, right? We should have, that point is a free edge. We should have a 0 shear flow at the free edge. Now, other point, this one here at the bottom. Okay? So this point corresponds, this point here corresponds to my variable S equal to H. Very good. S equal to H. So if I replace here S by H, I will get H squared over 2 minus H squared over 2. That is 0. Right? This means I will also get a 0 shear stress in this section, which is also free edge, so my shear flow should be 0 as well over there, right? So this is a good way to check if your calculations are correct. Free edges is always a good one. Now let's check this other point here at the neutral axis. This point at neutral axis, my S variable is equal to H over 2. So if I replace in this equation, I will get here what? H squared over 4 minus H squared over 8, right? This gives H squared. So this is 2 over 8, right? Agree with me? So we can then say that the shear flow at this cross section, I'm going to put it here. I'm going to put, this point here. I'm going to say my shear flow at this point for S equal to H over 2 at neutral axis is going to be equal to minus Vy over Iz times the thickness times H squared over 8. Right? And then I can do something like this. I can say that the distribution of my shear flow right? Why did I do a distribution like this? Well, first I have 3 points and I know it needs to be quadratic because I have here a quadratic term on S, right? So this is a function which is quadratic on S. So quadratic distribution is this one. The value of the shear flow at neutral axis is the maximum shear flow you have in the cross section, and it's equal to this. Right? At the free edges, these 2 points, I know that my shear flow needs to be 0. We confirm that from the equation that shear flow is equal to 0. So you have 3 points. You know the distribution is quadratic. You just draw a quadratic or a parabola, a quadratic curve passing on these 3 points, and you have the distribution of the shear flow. All right? So this is a very basic example just to show you very quickly the application of the transverse shear flow equation. So this is an open cross section. So open cross sections are, like I said, I shape, L shape, can be cross sections like this. For example, in the wing you have what we call the stringers. Basically they are stiffeners, right? So you have, for example, if we have a wing cross section, we have the spars, which many times are I-shape or C-shape. Let's see, for example, a big spar you have here inside, which is a C-shape, right? It goes all the way on your wing. But you also have what we call stringers. Usually they have the shape of a Z. Z stringers. Basically they are stiffeners. Because don't forget that in aircraft structures, we always want to use the minimum thickness, the minimum material as possible because of the weight, right? We want to save weight. So this is really very well optimized. So the understanding of the shear flows, these kind of things, needs to be done very, very well. Otherwise, something very nasty can happen, right? So these Z stringers, basically they are stiffeners. So because the skin only, if you have skin without these stringers and spars and ribs inside, this skin will buckle, will collapse, right? So you need to have inside these stiffeners to give some stiffness to the entire wing, so that its deformation is controlled, right? So this kind of cross sections, that they are what we call open cross sections. They are always open because they always have a free edge, right? So we can do for example, if you look at this spar, we can say this is my free edge here. We can say our S variable starts here, and then our shear, it flows along this part in this, like this, right? Shear flow. For example, if I have an I-shaped cross section like this, what is going to happen with the shear flow? So this is the neutral axis here, for example, right? So how are we going to do our analysis? Okay, we have a lot of free edges in this I shape, right? So for example, we have a free edge here. So we define a local variable, let's say S1 in this free edge. Then what is going to happen to the shear flow? It will start flowing from this edge and it will arrive here at this point. Now, we have a problem here. We cannot continue from here because why? Because some shear flow is going down and some shear flow is going to the left after reaching that point. You can imagine this like water flowing in a pipe, right? Part of water is going horizontally and part of water will go down, right? There is going to be a bifurcation there, right? So we have a problem here. So how do we do after this point? So what we have to do is, well, we have another free edge, is this one. So we can define the second local variable, S2. And we can use that equation we have been using with these new local variables. And then what is going to happen is the shear flow will flow from this point. So they will meet here. And then the only option we have here is that for the resultant of these two shear flows, they will be combined and they will go down here, all the way down. They will arrive this point and part is going to the left, part is going to the right. And then what you have is, you have in this cross section, you have a distribution of the shear flow, basically shear flowing around the cross section, right? So we are going to do this analysis. Let me see if I have a simple example, because we don't have too much time. Let me see if we have a very simple one. Okay, so what I'm going to do is, I'm going to stop this recording now, and I'm going to use the visualizer to show you very quickly, because we don't have too much time, to show you one example that I have here with me. We go just very quickly through this example, and then next week we continue with this process, okay? So basically next week what we are going to do is, we are going to do some more examples on this, and then we are going to analyze closed cross sections, which is more difficult. Unfortunately, our life will get more difficult. But we will try to make it easier, okay? So I'm going to finalize this, and we will continue in the visualizer, all right?